Okay, this is going to be a much shorter video. It's going to be the continuation of the notes from the last time. This is page 14, and we're only going to do page 14. And then the rest we'll do in class for page 15, 16 on Wednesday. Okay, a washer. And let me move my face out of the way. So like your face is in the way. A washer. So a washer is when there's a gap in the solid. So basically the cross section would look something like this. A hollow circle. In the last video, we were working with discs that were not hollow. The cross sections in this last section were all whole circles. But in this section, we're going to get some washers, some circles that are going to be hollow. Now, the formula that you can use to help you with this is going to be equal to, again, we'll do x equals a to x equals b. And we're going to do a function minus axis rotation, so minus axis. We'll square it because it's the radius squared, pi. And this time we're going to call this the big radius. We're going to subtract to it after I put the dx, thank you Andy, and we'll subtract from it x equals a to x equals b of the function minus the axis squared dx with the pi in front because that's the area of a circle, and this is going to be a little r. So the whole idea with a washer is that there is a big radius, and the big radius starts from the top and goes to the center, and then there's also going to be this little radius. And this little radius is going to be starting at the top of the little circle and going to where the axis is, going to the center. So that's why we're going to need two integrals. In this last one, since we only had solid discs, we only had top to the center, which is why this whole part could just be called the big radius. And again, this part didn't really matter, but just to streamline the idea, I wanted to make sure that we were actually having that other option. With discs, though, you won't actually have this last part. But it would be good to know that anyway, because if you know there's no r, you know that there's no second integral. So discs, just to remind you, there is no little r, because discs are solid. They're not hollow. So no little r means no second integral. Okay. Going back to our washer though. So this will have a hollow part. Let's see why, and I'm only going to draw this out once. So this was the same as number 4. And I think we started it the last time. We're going to get this blue line inverted, and this is a sketch. And we'll get, let's see that in blue actually. Yeah, boy. Oh, hold on. Aha. This is erase this guy. Okay, so here is this blue line. And then we'll get that purple parabola underneath it, so something like this. And the area that's going to be bounded between them is going to be that shaded part. And what I'm trying to go for here is there is going to be a hollow part. That hollow part is in the center. And it's really important for you guys to understand. Now, you don't have to draw the inverted part necessarily. The inverted part is just showing that there is a 360 degree reflection, 180 degree rotation of this area to over here. And the only reason I do that is to emphasize that there is a big circle, purple connecting to purple, and there's also a little circle, blue connecting to blue. And that's going to tell us that there is a bigger radius and a smaller radius. And the bigger radius is going to start at the top of the function and go to the axis of rotation. And that's really important. We're going to the axis of rotation. and the axis of rotation is around the x-axis, so we're going to y equals 0. So we're going to have, and f of x is purple, we're going to have the integral from x equals, it looks like 0 to 2, x equals 0 to x equals 2 of, now we need a pi in front because this is going to be the area of a circle. The integrand will be f of x, x squared plus 2, minus 0, and we'll square it. Now that would get the full amount of area everywhere inside. But because there's that hollow part, and that hollow part is going to be this part here. This is all hollow. So because that part is hollow, we have to subtract off the accumulating area from that part. So the way we're going to do that is we're going to subtract off a pi because we're doing the area of a circle. Same limits of integration. And now what we're going to subtract off, this was g of x, and top to bottom, the function to the axis is going to be g of x minus 0 squared dx. And that's it. And it's really the same thing every single time. I'm going to erase this coloring, so hopefully you have that jotted down, and if you don't, pause the video. And then I'm going to go and do just one more with y equals negative 1. And then I'm just going to pick up some speed so we can finish up this video quickly because the last one was kind of long. Okay, so here's y equals negative 1. Now, we still have that function, but we're going to be reflecting around y equals negative 1. So we're rotating around y equals negative 1, which means with that this blue will now be at 3, something like this. And then we'll have the purple, that will be something like this. And the only thing that changes here, and again, the reason I took the time to color this, the only thing that changes is that the purple circle is now a little bit wider than before. And that blue circle is a little bit bigger than before as well. And all that means, and again, the formula covers this if you're not understanding, all that means is that your big radius is starting at f of x, but instead of stopping at x equals 0, we're going to paint all the way down to that blue line, to that axis of rotation, around y equals negative 1. So we're going from f of x to the axis. And the way it's going to work, and if nothing I'm saying is making sense, I think this should make sense now. We're going to get x equals 0, I hope, to x equals 2 of, it's still going to be f of x because that's my top function in purple, to the axis of rotation, which is minus negative 1 squared. We're squaring because we have a radius. Radius times pi, radius squared times pi gives you the area of the circle. Integrating the area of the circle gives you the volume of the solid. That's why all of this math is coming together. And then we're going to minus something very similar. We'll put a pi in front, x equals 0 to x equals 2 of g of x, because again, we're going to start with g of x. And we're not stopping at 0, we're stopping at negative 1 this time, because that's the axis of rotation. So we're going to have g of x minus negative 1 squared dx. Around the line y equals negative 2 won't be much different. So now I'm going to pick up some speed here. We're going to get pi times the integral from x equals 0 to x equals 2. And we are dropping the function this time down to negative 2. And I'm just going to clear this off. And it's going to be the same setup. So feel free to skip ahead in the video to get to the next one. It will change slightly for a later one, so make sure you pay attention to that and get the right answer. But if we're drawing to y equals negative 2, and this time I'm not going to draw the reflective part, I got a big radius, and then I have a smaller radius. And the big radius is going to be that same function f of x, but now I'm minus negative 2 out of it. And then I'm going to be subtracting off that smaller circles, which has a smaller radius. of g of x minus negative 2. And we got to put that in parentheses, we got squared, and that's it. Now for number 7, 7 and 8 are a little bit weird because 7 is above the function. And if I go to 7 here, here's y equals 7. I'm rotating this now around y equals 7, and it's going to change slightly because the hollow part is no longer below, the hollow part is now above. So hollow is now above and not below. And I don't really try to remember this with a formula necessarily. Like, I don't try to remember, oh, when axis of revolution is above the curve, then I need to change the formula. When axis, I'm always looking at the picture. So hollow part above, and let's draw our radius. Our big radius here is going to be from the axis of rotation to here. Now the formula that I gave you is slightly different. The formula says function minus x-axis. Interestingly, if I do the function minus the x-axis, I'm going to get it right. What big R is equal to here is going to be the blue, which I believe was g of x. Let me just write that down. That's g of x. Oh, that's not blue. So the blue is g of x, and maybe I should use blue here for the big radius. And this time the little radius is going to be from the axis to purple. And again, the purple is f of x. So the big radius. The big radius is going to be 7 minus g of x. The little radius is going to be 7 minus f of x. Okay, when you write out your formula, this is what's interesting. Your volume is going to be equal to the integral with the pi in front from x equals 0 to x equals 2 still of 7 minus g of x quantity squared dx. And it's still going to be minus pi times the integral from x equals 0 to x equals 2 of 7 minus f of x quantity squared. Okay. You don't actually need to write it this way. You could also write this integral as, and I'm going to write it down here, actually I'll write it up here for you. You could also have this integral as the volume is equal to x equals 0 to x equals 2 with the pi in front of g of x minus 7. Okay, that's nothing. G of x minus 7 squared dx, and then minus the pi times the integral from x equals 0 to x equals 2 of 7 minus f of x. I'm sorry, f of x minus 7. That's what I want to say. And the only reason I'm writing this formula down for you, not this formula, this different setup down, is because if you are stuck in the pattern, if you just really get the pattern and you don't like changing it, there is an alternative. Because I told you that the volume of a washer is going to be the function minus the axis squared minus the function minus an axis squared for a big radius and a small radius. And if I switch the axis minus the function, that's going to be a little bit confusing. But you will get the same answer, and I challenge you to understand why later on. You would get the same answer if you put function minus 7 squared, function minus 7 squared, even if the hollow part is above. The difference is you have to remember which one is your big radius and which one is your small radius. And with that, we'll finish up with our last one here. We're rotating around the line y equals 8. Since 8 is just one higher, we'll notice that there's not going to be much difference. And I'll write my answer as volume is equal to pi, x equals 0 to x equals 2 of, and I'm going to open big brackets here. I'm going to put a g of x, because g of x is the longer segment here with to the axis of rotation. So we'll do g of x minus 8, and we'll square that. And then we will subtract off f of x minus 8, and we will close a big bracket and a dx. And the only reason I'm writing it for you this way is I want you to be aware that you could just write this as one integral, since we're bounded in the same limits of integration. I wrote the integral separately, just so that we were clear that we were taking two different parts and subtracting them. It would not be wrong to write it with one integral, though. It's just a little bit more tedious to, well, this whole thing is tedious to evaluate. The other way you could have written this, if you weren't comfortable with changing the order here, some people see it more logically as x equals 0 to x equals 2 of everything that I just said before, but a little bit backwards. 8 minus g of x squared minus 8 minus f of x minus f of x squared, close big brackets, dx, and that takes care of it, guys. Thanks for watching the videos.